everyone. Welcome back to the lectures on Introduction to Multi-Agent Systems. In today's lecture, we'll study about equilibrium points and their stability notions. We did discuss in what equilibrium points are in the previous lecture, but we did not really discuss anything pertaining to their stability. In general, an equilibrium point is a point such that if a solution starts there, it continues to remain there. However, what if we perturb the trajectory slightly from the equilibrium point? Will the trajectory move closer towards the equilibrium point, or will it move farther away? These are some important questions which help us answer the question of whether or not an equilibrium point is stable. So this will be the first part of today's lecture. In the second part of the lecture, we'll talk about Lyapunov stability. So in the first part, we'll discuss something that's known as epsilon delta stability. We'll figure out equivalent conditions using something that's known as a Lyapunov function in the second part of the lecture. So this is a very, very important topic because using the points discussed in today's lecture, later on, we'll study a lot of applications of multi-agent systems, say like formation control or rendezvous. In all of these applications, the distributed rules that we design, we can show that the guarantees that these distributed rules work or they do not work. All of these rely a lot on Lyapunov stability-based rules. So let's get started and try to understand these concepts. So how exactly do we define the stability for an equilibrium point? To begin with, we still have the same underlying framework. Let's say x dot of t is equal to sum f of x, t, and say u. This is the representation of a nonlinear system. We will now make a few assumptions here, and we will justify why we are making those assumptions. The first assumption goes as follows. We claim that the system is autonomous. The reason being that this is just the initial analysis, and the structure of an autonomous system makes the analysis slightly easier. So what does the autonomous system look like? It looks like this. X dot of t is equal to f of x of t. This is the autonomous form of this equilibrium point. Furthermore, we make yet another assumption. So just so that we don't get confused, I'll just mention here that these are the assumptions. So this here was our first assumption. And our second assumption is, so obviously we want the system to have a unique solution. So we assume that f, this is an important assumption, f is locally Lipschitz in the domain D, or we can write over the domain D. Notice here that we did not have to specify that it must be piecewise continuous in T. The reason being that f, as you can see, is a function of x alone directly. So this is a very important assumption because this is required to ensure that we have a unique solution for the system. Now we characterize and study the stability of a given equilibrium point. So let x bar be an equilibrium point. Let x bar be an equilibrium point of the system x dot equals f of x without loss of any generality. we assume that x bar equals 0. Let's highlight it in a slightly different color. X bar equals 0. This does not change, or this analysis, this assumption is not stringent at all. The reason being that, let us say now, the equilibrium point x bar for any given system, obviously it does not necessarily need to be equal to 0. And suppose it is not equal to 0. What would we do in that case? In that case, all that we need to do is, let's write it here. Suppose x bar is not equal to 0. Then we simply change the variables in the system. We define some other parameter, say z, such that z is equal to x minus x bar. Then the z dot is, remember that x bar is the equilibrium point, so it is a constant value. Hence, its derivative is 0. So z dot is equal to x dot alone. And what is x dot? It is equal to f of x. F of x, again, can be written as z plus x bar. When we do a Taylor series expansion of this, eventually, or see, this can always be expressed as a function of z through a Taylor series expansion. The reason being that we must remember that since x bar is an equilibrium point, it implies that f of x bar is equal to 0. So we can substitute this here in the Taylor series expansion, and ultimately z dot boils down to this value equals gz, where when x is equal to x bar, z becomes equal to 0. Hence, our new equilibrium point z has now shifted to the value 0. Let's write it. This further implies that g of 0 is equal to 0. Hence, a simple change of variables solves our purpose. If x bar, the equilibrium point, is not equal to 0, then we define a new variable z as x minus x bar. In that case, z dot becomes equal to x dot minus x bar dot, but x bar is a constant, so its derivative is equal to 0, hence this remains equal to x dot alone. X dot is equal to f of x. F of x can now be written as f of g plus x bar. So we are simply replace the value of x by bringing x bar to the RHS in this equation. Notice that since x bar is a constant, we can write this or define this as some function now of z alone, that is the only variable. And what happens to the equilibrium point of this new system? In the transform domain, we have z dot equals gz equals 0. We are trying to check if z equals 0 is a valid equilibrium point. So rather than writing 0 here, let's write g of 0. What is g of 0? G of 0 is nothing but f plus z is 0, so f of x bar. And since x bar, so we know that f of x bar is equal to 0 from here. Hence, what we get is z dot is equal to 0 when z is 0. Hence, z equals 0 is an equilibrium point. So that is why we say that this, or without loss of any generality, we can say that the equilibrium point of the system is at origin. Having said that, now let's try to characterize and study the stability of the equilibrium point x bar. With that, we introduce our first notion of stability, known as the epsilon delta stability. What is the epsilon delta stability? So we introduce the first definition here. We say that the equilibrium point x equals 0 of the autonomous system x dot equals f of x is, the first point is stable. When is it stable? It is stable. Let's highlight this slightly better by writing it here. So the equilibrium point x equals 0 is stable if for each epsilon greater than 0, there exists a delta greater than 0. This delta is dependent on epsilon. Such that if or whenever the initial condition is, the norm of the initial condition is bounded by this factor delta, it implies that the trajectory for every time instant, its norm is bounded by the term epsilon. This holds for every t greater than 0. So let us try to understand this definition one more time. It says that the equilibrium point x0 of the system x dot equals f of x is stable if we can find this pair epsilon and delta. And remember that we start by choosing an epsilon, and correspondingly we find a delta which depends on the chosen epsilon. We say that whenever we start within a delta ball of the initial conditions, for every instant of time, the trajectory remains bounded within some epsilon ball. So just to give an example, let this be our domain. And this is the initial condition. Let us draw two circles here now, two discs rather. This is the first one. Let this have some radius delta. Then we say that we can draw yet another ball now, which is the epsilon ball. This value is epsilon. Suppose the trajectory starts within the delta ball. As it evolves over time, it does not escape the epsilon ball. So this is what, and this, the outer circle here is nothing but the domain. This is the notion of epsilon delta stability. So basically, in some ways, it says that the trajectory does not go unbounded. It doesn't say anything about convergence. It doesn't say that it converges to some equilibrium point or something. No, it simply says that the trajectory does not go unbounded. So this is the first notion of stability. We can say a few more things based on this definition. We can say that the equilibrium point is unstable simply if it is not stable. Not stable. Moreover, so it means that we are unable to bound the trajectory. It keeps going unbounded. Hence, in that case, the equilibrium point is not stable. Furthermore, if the equilibrium point is stable and it exhibits some nicer behaviors as well. Let us write it first. We say that asymptotically stable. Asymptotic stability says that, or let's put it this way, the origin is the equilibrium point of x dot equals f of x, and that origin is asymptotically stable first if it is stable and furthermore delta can be chosen such that whenever we start within, so just a moment, here instead of x0, this should be equal to the origin x bar, and x bar equals 0 here. Please take a note of this. Then we say that, coming back to asymptotic stability, for asymptotic stability, the first condition is that the origin must be a stable equilibrium point. Additionally, delta can be chosen such that whenever we start within some delta wall around the origin, it implies that as time tends to infinity, meaning at steady state, the trajectory always tends to the origin. This is a stronger condition. In the epsilon delta stability, we only said that the trajectory remains bounded. Here we say not only does the trajectory remain bounded, it also tends to the equilibrium point at steady state. Let us quickly see some examples of simple systems. Let's start with the same autonomous system that we've been talking about. Now let us say that x is a scalar and not a vector. Suppose we've been given some trajectories of this system. Let us consider a few different kinds of trajectories. The first one is, say, let's draw the axis first. And let us look at two different cases, sorry. Along this, we will plot two different trajectories and we'll try to see if the origin is a stable equilibrium point or not. The first is, say, this. In both the cases, we have x along the abscissa and f of x along the ordinate. Suppose this is the trajectory in the first case. So I'd ask the students to pause the video here and tell me if they think the first plot here. In this plot, is origin a stable equilibrium point or not? If it is stable, then why is it stable? Please pause the video right here and try to think about that. I hope you've now tried it. So I've drawn yet another curve here. Okay, so now we have two different trajectories, and now we'll try to figure out whether the system is stable or not, and whatever it is, why does it behave this way? Okay. Or why do, okay, let's start with this f of x. The first one, let's write it as some a and b. Now in figure number a, we see that suppose we take some neighborhood, let me zoom this in, we take some neighborhood very close to the origin. In this neighborhood, suppose we are at some point here. At this given point, what is x dot? X dot at this given point is greater than 0. So what happens to x? We see that x keeps on increasing. So we move along increasing values of x. And what happens, let's say now we consider a different point, maybe somewhere here. X is already a negative value, and we say x dot. And we see that x dot equals f of x, and f of x is now a negative value. Hence, x dot is less than 0, meaning x keeps on further decreasing, meaning we now keep moving in this direction. That means, suppose we start at the equilibrium point and get perturbed slightly to the right. Then, since x dot remains greater than 0, we will keep on moving in this direction. And we will move farther and farther away from the equilibrium point. And it'll keep on increasing because x dot will continue to remain greater than 0. Similarly, again, if I start at the equilibrium point and get shifted a little to the left, again, x dot, which is equal to f of x, continues to be less than 0. Hence, we keep on moving in this direction. Meaning, it is not possible for us to now bound the trajectory within some finite values. Hence, according to the epsilon delta notion of stability, the first system here is actually unstable. What about the second system? Again, let's extend the arguments to this system as well. We start with some neighborhood close to the origin. Now, let us mark again, as before, two different points. Say this is one of the points. At this value, we see that x dot, let's take these points a little bit farther so that we can clearly see things on the figure. And say this is my x, where I'm checking what happens to x dot. X dot now is less than 0, meaning x, we start with an x which is greater than 0. For every x greater than 0, we see that x dot, which is equal to f of x, is less than 0, meaning we will now move towards the origin, which is our equilibrium point. And as soon as, so if I start here, I'll keep on moving towards the origin. As soon as I reach the origin, I know this is my equilibrium point, so I'll stay put here. Similarly, let me take a point on the left. We now see that x dot here is actually greater than 0, meaning
for this point, while x is less than 0, x dot is greater than 0. This means that x actually keeps increasing. Meaning now, if I start on the left, I keep moving right towards the equilibrium point again. And as soon as I reach here, I continue to remain there. Meaning, wherever I start from, it doesn't matter wherever I am, I'll always move close to the equilibrium point. Hence, in this case, the equilibrium point is a stable equilibrium point. This is a stable equilibrium point. Let me ask a question here. Is the system depicted in figure B, or let's change the question slightly, is the equilibrium point for the system depicted in figure B, is it asymptotically stable? The answer to this question is not difficult, so I'll leave it for the students to figure out. With this, we will now introduce yet another notion, or two more notions rather. The first is that of a region of attraction, and the second is of global asymptotic stability. So let's get started. So we already had first definition here. Let's look at the second definition. We start the definition by saying that suppose or let the origin be an asymptotically stable equilibrium point for the autonomous system x dot equals f of x. And we have the same assumptions that f is locally Lipschitz in the domain. Over a domain D. Then we can say the following things. First is we introduce something that's known as a region of attraction. What is a region of attraction? It is the set of all points x naught belonging to the domain such that let's write it this way, such that limit t tends to infinity, x of t converges to the origin. This is the notion of a region, the region of attraction. It simply states that it consists of all those points x naught belonging to the domain such that whenever we start from that point, okay, let's define it. Whenever x at t equals 0 is equal to x0. Again, let's look at this definition one more time. It says that the region of attraction is simply the set of all points x0 belonging to D, such that whenever we start from this x0, we are always driven to the origin. To explain this graphically, suppose wherever we start from, let me mark some axes here. The trajectory from each of these points always moves towards the origin. The arrows are always towards the origin. Then all of this region, let us say, I can now say that any point, if this is my larger, this one is my domain, and the one inside is some set, perhaps C. If I can say that every point in C, if that is the initial condition of the system, then the system is always driven to the equilibrium point, then every point or this entire set forms the region of attraction for the origin. Furthermore, with this, we now define one more notion of global asymptotic stability. Or let's say globally asymptotically stable. We say that the origin x equals 0, we started by saying that it is asymptotically stable. When do we say that it is globally asymptotically stable? Obviously, if wherever I start from, it doesn't matter, whichever point it is in the domain, I'm always driven to the equilibrium point. Then we say that such an equilibrium point is globally asymptotically stable. In this case, we can simply say the region of attraction is the whole domain. D. Let us now define yet another notion. Although we started by saying we'll just talk two, but I must mention yet another important concept here, that is pertaining to something that's known as exponentially stable or exponential stability. But we say that the origin is an exponentially stable equilibrium point if few conditions hold, that is, norm of x of t can be bounded above by something of this form. E raised to the power minus lambda t, and this condition must hold for all time or for every time greater than or equal to 0, such that the constants given here must satisfy a few conditions. First, k must be greater than or equal to 1. Lambda here must be greater than 0. It must be greater than 0 for all initial conditions within a certain bound C. So effectively, let's zoom into this expression one more time. Effectively, it says that k is greater than 1, greater than or equal to 1, and this lambda here is greater than 0, meaning this is actually a decaying function, and x, the norm of x, is bounded above by a decaying exponential. So what happens as t tends to infinity? what happens to e raised to the power minus lambda t? It goes to 0, meaning eventually this norm here also has to go to 0, meaning if a system is exponentially stable, then let's write it. This straightforwardly implies a few things. Limit t tends to infinity, x of t is directly equal to 0. Why? Because it is bounded above by a decaying exponential, which again goes to 0. So please remember that norm is a non-negative scalar. Hence, when we say that norm is bounded above by 0, then the only value it can take is equal to 0. Hence, and the only time when the norm of this can be equal to 0 is when it is equal to the origin itself. Hence, this is the first condition. Further, what does this imply? It implies that, so notice here that this is exactly what happens in the case of asymptotic stability, meaning, hence, the origin is also asymptotically stable. Meaning exponential stability implies asymptotic stability. Vice versa is not always true. So what additional information do we get when we say that the equilibrium point or the origin is exponentially stable? We have now bounded the rate at which it converges to the origin. That is the only difference. So this is how we can characterize all the equilibrium points of the system pertaining to their stability properties. With this, we will introduce now the notion of Lyapunov as well. So what have we talked about so far? So far, we have discussed that under what conditions an equilibrium point is first of all stable or asymptotically stable or exponentially stable. But in most of these conditions, if we zoom in, let's look at the first definition we saw, which was of epsilon delta stability. Here, again, we had to figure out whether the entire trajectory, meaning the trajectory for at all times, whether it was bounded or not within an epsilon ball, as also explained through this figure. Again, for asymptotic stability, we had to do something similar. We had to check not only was it bounded, it also converged to the origin. Similarly, for exponential stability, again we impose the condition, let's go here, again we impose the condition on x of t, meaning all of these notions require us to have some knowledge of x of t, which is not a very practical thing. We may or may not always be able to solve nonlinear equations. Is there any other technique that can actually help us figure out these properties pertaining to the stability of equilibrium points? The answer to that is yes. And we'll do that using something that's known as Lyapunov functions. So let's get started with the Lyapunov functions.